let's look at something called the common ion effect. I love the common ion effect. We want to calculate the solubility of silver dichromate in water and also in a solution of silver nitrate. Sounds like a blast. Let's do the solubility in water first. This one will be pretty straightforward. If we wanted to write kind of an expression, I would have the original solid, the silver dichromate. It would dissociate a small extent, and we'd have 2 silver ions and a dichromate ion. Cr2O4. This is a -2 ion. And if I wanted to, I could put in maybe like some phase symbols. We're looking at the solubility of that original solid. What's its tendency to form ions in solution? Aqueous. All right, so we've done some kind of like this. They do give me the KSP value. And I know that like some of this original solid will dissociate. Some of it will dissolve. So we could just say it's going to go down by X. This will go up by 2X. And this will go up by X. So I just want to solve for X. That is the solubility, the amount of the original compound that dissolves. So we've got K. 9 KSP. 9.0 times 10 to the -12 equals products over really nothing, because that's a pure solid. So we're not going to include that in our equilibrium expression. That's why they call it the solubility product. Or sometimes you might even hear it called an ion product, because it really is like a product of the ion concentrations. This will be 2x squared times x to the first. That should give me 4x cubed. So we'll solve this sucker for x. Maybe leave 2 sig figs, something like that. X is about 1.3 times 10 to the -4th. You could say moles per liter. You could say big capital M molarity. 1.3 times 10 to the -4th moles of that original compound will dissolve in a liter of water. So we'll make note of that. That's the solubility in water. Excellent. Well, that wasn't so bad, huh? That was almost kind of fun. Okay, let's do the other one. What if instead of dissolving the solid in water, we dissolve it in a solution of silver nitrate? Don't touch it. That's the one that gives you like little brown, freckly spots all over your skin. You'll notice it like a couple hours later. Okay, so here's the second part of this. I'm looking at the same compound, so I can start it off kind of the same way. I would have that silver dichromate in solution, forming 2 silver ions plus the dichromate ion. This would be a really bad one to like lick your fingers if you were dealing with this solution. Silver ions and chromium ions. Yucky. There we go. Okay, so we know that the original compound will dissociate. If I wanted to, I could put phases in. You don't have to. I'll just put them in for kicks. All right. So yeah, this original guy, this is going to go down by a certain amount. This is going to go up by twice that. I'll form 2 silver ions. And this will go up by X. 1 dichromate ion. Here's the difference. When we dissolved this stuff in water, it was just water. We didn't have any silver. We didn't have any of that dichromate. Here's what's called the common ion effect. By dissolving this silver dichromate in a solution of silver nitrate, we have a common ion. They both contain silver. The nitrate is a spectator. There is no nitrate anywhere in this expression, but we do have silver. So when I put this thing in a solution of silver nitrate, it's almost as if like we can add 0.1 moles of silver. So maybe here I could put this in as like plus 0.1. I think it was 0.100 molar. Maybe I'll move this X over a little bit. We're getting kind of cramped. Does that make sense? We're not adding it to water. We're adding it to a solution that already has silver. It already has 0.1 moles of silver. Now, to that, we'll add some more silver. By however far this goes forward, 2x, we're going to have a substantial amount of silver in the final solution. That original 0.1 moles from the silver nitrate solution plus 2x, a little bit of silver from the dissociation of this silver compound. Let's solve this thing for x. Watch what happens here. And this is beautiful. We have the KSP. It's the same. KSP. Was it 9.0 times 10 to the negative 12? My ion product's going to look a little different. This is going to be 2x plus 0.1. Or you could say like 0.1 plus 2x, obviously. And we need to square it times x. Ooh. Icky. Do you think we could use the 5% rule? Absolutely. So we're going to add a little bit of extra silver, but probably not much. That K value is really small. So I could make my life a little bit easier by getting rid of that plus 2x. I've got 0.1 moles of silver from the original solution. That's going to be a lot more than whatever 2x is. Yeah, I'll get a little bit extra silver from the dissociation, but it's going to be so small that it's probably insignificant. And getting rid of that 2x makes my math much easier. So now I can plug this in, solve for x, and I get, how about 9.0 times 10 to the negative 10th. And then that could be moles per liter, or big capital M for molarity. That's the solubility in silver nitrate. Okay, this is interesting. I like this. Check out these solubilities. It's a lot greater in water. When I put that silver nitrate in a solution that already contains silver, the solubility drops substantially. We get to revisit our old friend, Le Chatelier. This is a good example of Le Chatelier's principle. Yay, we haven't seen you for a few weeks. Welcome back. Le Chatelier's principle, if you add something, you shift away from what was added. We're putting this silver dichromate into a solution that already has silver. Like, we're adding silver to silver. If we add something with excess silver, we shift away from what was added. So by putting this compound in a solution that contains a common ion, you will always reduce the solubility. If I would have added this to a solution of like sodium dichromate, it would have been a real similar outcome. Ooh, there's already some dichromate ions. If you add something, you shift away from what was added. So that's kind of the concept of the common ion effect. If there's a common ion in the solution, it will always reduce the solubility. Now, sometimes it can actually be a good thing. I don't know if you've ever had to have like a really crazy like internal x-ray or anything like that, where sometimes you have to drink this really chalky stuff. It's really nasty. It's barium sulfate. It's kind of chalky and gross because the barium sulfate is only marginally soluble. So you'll see it kind of as like a white, almost like a thick, milky solution. Now, it does have the tendency to dissociate. You would form barium ions and sulfate ions. Excellent. Now, here's the problem. That barium sulfate can be used to do like internal x-rays, like internal organs and stuff like that. The x-ray will pick up the barium sulfate, but you don't want it to dissolve. Barium sulfate solid, this is harmless. This is okay. Eventually, this will just come out when you go to the bathroom. Not to be gross or anything. Sulfate ions are totally harmless. Totally harmless to the body. It's this guy. We don't want barium ions swimming around. Barium is toxic. So like we use this barium sulfate because it works well on x-rays, but we can't let it dissolve. We don't want it to dissociate because you're going to have these toxic barium ions swimming around. So to prevent the barium sulfate from dissolving, we usually add a common ion. So to the barium sulfate, they'll probably add something like sodium sulfate. So they'd have barium sulfate plus sodium sulfate. You drink it, sometimes like they'll also put you to sleep for a little while. But by adding something that already contains sulfate, we're increasing a common ion. By adding something, we shift the equilibrium away from what was added. So we kind of force that barium sulfate to stay as a solid. Interesting. So what you end up drinking really is like a mixture of barium sulfate and sodium sulfate. The extra sulfate is a common ion. And by adding a common ion, we shift away from that ion. So it reduces the solubility of the barium sulfate, which in this case is a good thing. Not that this is like on the test or anything. I mean, maybe it's on the test. I don't know. But it's just kind of a good example of the common ion effect, where a common ion will shift away, usually toward the solid, reducing the solubility of the original compound.